So, morning everybody. We are going to be starting energy today. All right, we're going to start and finish energy today because it's not a very long topic, but it's a very important topic. So, this is our mechanics tree handout. There are three handouts that we have in the mechanics topic. And this handout, we're going to look at work, energy, and power. But today, we are just going to look at work and energy. So, starting off with work. All right, so what is work? Work in scientific terms is the mechanical transfer of energy to or from a system by the pushes or pull of an external system. Meaning, work is simply the amount of distance a force travels. If you cannot make a force travel, you cannot make an effort, being a push or a pull travel, right? You will not have done work. And how do we calculate work? Is really, really simple. Work is simply force by distance. And if we were to put it into symbols, work is always in a W. There's no other symbol that goes for W. Is your force by distance. Now, here we have displacement, and it is not uncommon to see you write this as force by distance. Either version is okay. Please note that the unit of work is the joule. So this is a brand new unit of, well, a brand new unit. All right, and joule is the unit we are going to use throughout this topic in work and energy. So first thing to remember, we have work. Work is simply the amount of force that is applied to an object while it is moving. If an object does not move, you are doing no work. Doesn't mean you're not expending energy, but it means that you are doing no work. All right, so moving on. So if the force, continue reading from our handout, if the force does not move over a given distance, then no work is done. So what we have, if you take, say, a box, and you were to push that box, the distance that you travel while pushing that box will be the amount of work that is done. But if you stand up, suppose you are standing up and there is a big wall, right? And you decide to push on that wall, you are not moving. The wall is not moving. Doesn't mean you're not going to expend energy. Your arms are going to get tired. You're probably going to slip and hit your head, which is very funny, but that always does happen. All right. If you are not moving, if your distance is equal to zero, then work is also equal to zero. The only way we can do work, right? Now, we're not talking about doing schoolwork. All right. We're talking about physical, mechanical work. This is the topic of mechanics. All right. And when we do physical, mechanical work, all right, we can only do work if we move our object. Moving on. Moving on to energy. I like to say this. This is not something you're going to find in a textbook, but physics is essentially the study of energy. That is all it is. If you come down to the very, very basics and somebody tells you or asks you, what is physics? And is a non-science person. Like I remember my grandmother asking me, um, what subject you're teaching again? Or what you're doing a degree in? And I said physics. And she was like, she had no idea what physics was. So if you had to explain what physics is in the very simplest of terms, it may be a little wrong, but very, very simplest of terms, physics is the study of energy and how the different forms of energy move, the rules and laws and theories that govern it. So there are many types of energy that one can encounter. We're reading from the handout. And all forms of energy are measured in joules. As I said, this entire topic of work energy, everything is measured in joules. It's not measured in degrees Celsius. It's not measured in meters per second. It's measured in joules. So let's look at this here, where we have our different forms of energy. All right, so different forms of energy. If you look at here, we have kinetic energy, we have potential energy, Let's get a little bigger for you all to see. All right, we have elastic energy. As in elastic energy, if you take a spring or a string or something elastic and stretch it and you let it go, it's going to fly all over the place. So that means it has some sort of energy in it. We have sound and seismic energy. We have light, electromagnetic waves such as radio waves, ultraviolet, X-rays, and all of those things. These are other forms of energy. Electricity is a form of energy. That's the most common form of energy in our modern society. Magnetism, heat, nuclear energy, exothermic and endothermic reactions. You all know that in chemistry. People, are you all having issues with internet? I see people keep bumping off and coming back on.
I can't talk for me, but I know that some people does have internet troubles.
This morning, a few people are being bumped off and coming back in. So, again, if you all get bumped off and kicked out, that's okay. The class is being recorded and I will post it up later on today. So, if you were to look at see how these categories or how, where my pen go? Okay, there we are. All right, if we were to look at how these different forms of energy can be categorized, we can categorize potential energy, kinetic energy. Don't worry, we're going to go through what those are just now. And elastic energy are all what we call mechanical energy. Mechanical energy, just so. Mechanical energy is the energy that is used in moving an object, or anytime an object has to move or body or system has to move, it has mechanical energy. It's utilizing some form of mechanical energy. We have seismic and sound. Just to blow your minds a little bit, we all know seismic waves are basically what they have in earthquakes. A seismic wave is essentially a sound wave. So it's basically energy from the massive explosion. Again, as kind of the wrong word, but it's the best word to describe it. Anytime you have um, an earthquake, the energy from an earthquake comes from one particular point, and that energy radiates outwards like a sound wave, except through rock. Then we have light. We have light, electromagnetic radiation, right? Light is actually a form of electromagnetic radiation. We're going to go through that when we start doing modern physics, and all of these fall under the topic of electromagnetic waves. Then we have electricity and magnetism. Believe it or not, electricity and magnetism cannot exist without each other. All right, as in we create electricity with magnetism, and magnetism does not exist without electricity. All right, so it's a really nice interwoven topic. That's why they call it electromagnetism, because those topics are so closely wound together, they have to be considered in the same topic. We have heat. Heat is called thermal physics or thermal energy, anything to deal with heat. And believe it or not, heat is our most obvious form of energy that exists. Anytime we know something has some energy, we know it will do so by exerting energy or taking away energy or whatnot. We have nuclear energy. We all know about what nuclear energy is. We may not know enough about it, but we're going to go through that really lightly. And then the last one, you all are chemistry students, so that's why I put this in here. We have endothermic and exothermic reactions. Chemistry students, what is an exothermic reaction?
Exothermic, I think
Yeah.
it's one of the key components of yes, I can remember.
If you want, you could type the response too. All right, you all should
Or in
know.
an endothermic, the energy, the heat energy is taken in or absorbed,
Right,
and then an exothermic reaction is given off.
right. The simple way, right? Remember, I tell you, there's always some way, some weird little way I try to remember these terms. Exo means to give off heat. Exothermic means to exit. If you look at the word exit, and exo means, You'll basically the same words. So I remember it this way. Exo means to exit. So this means that heat is given off of your body, and the other one is the opposite. So endothermic means to pull in energy and to pull in heat. All right, so one gets cold and the other one gets hot. All right, so moving on. Types of energy. I think I need to zoom in a wee bit more for this one. All right, so we have types of energy. Let's look and see. We have in the topic here, this is why I say physics is basically the study of energy. Because if you had looked at your syllabus, you're going to realize that each one of these topics fall under a branch of physics. Now, chemical energy actually comes from not really nuclear energy, but it's energy of atoms. So if you look here, all of these topics are topics in physics. We have mechanics. So what are all five topics in physics? Mechanics, light and waves, thermal physics, electromagnetism, and modern physics. So that's our main topics. We do have a sixth one, but we're not getting into that today. That's quantum energy and quantum states. But that can even be, if you've ever heard of quantum energy, that everybody should have by now, that actually falls under nuclear energy. So let's look and see the different types of energy we have. Now, this is a really simple diagram. There are far more different types of energy if anybody can think about it. Sit down and think about where energy comes from, or where can you see energy being utilized. So let's start from the top. We have a moving car is mechanical energy, because mechanical energy is the energy found within moving systems. We have hammering a nail. Something simple as hammering a nail has a whole bunch of energy in it. One, that's to think about how much energy is contained in hammering a nail. One, you're going to be moving your hammer, so that's mechanical energy. Two, you all know when you hit that nail a few times, doesn't the nail get hot? Anybody ever notice that? Nobody here ever hammer a nail?
Yes, miss.
Right? If you hit like really hitting that nail, right? We're not talking about those who are really professional and you aim and you hit once and it goes straight in. It's all the special people. You know, we're talking about regular people who have to hit it a few times. If you hit your nail a few times, it's going to get hot. So we have mechanical energy, we have heat energy, and how do you know a nail is being hammered? We can hear it. You can hear it all through the house, right? Even if your door is closed, you can hear somebody hammering something outside. So look at the amount of energy contained in just a simple event of hammering a nail. You have mechanical, you have heat, and you have sound. Lots of different types of energy in all of these systems. So this is why I said this is a really simple diagram. We're going to learn how to determine or how to identify the different types of energy within every system. A moving car. We all know moving cars have a whole bunch of different things. We have mechanical energy, it's moving. We have chemical energy from the gas being burnt, right? We have sound because it's creating sound. We have heat because that engine gets very hot. That's why we have a heat shield between the engine and the cab. Tons and tons of energy within a car. We have thermal energy, so we can look at melting ice. Melting ice, how ice melts is strictly due to thermal energies. Heating food being it in a microwave, in a pot, on a stove, in an oven outside in the sun, in a solar cooker. All right, these are all thermal energies, or thermal means heat. We have electrical energy being our electrical grid or power lines, lightning. We have electromagnetic waves, anywhere from radio waves to ultraviolet to infrared to X-rays to gamma rays. That whole long line of energy is contained within electromagnetic waves. Then we have chemical energy. Chemical energy is where we convert um, the systems into by chemical processes into energy. So we know a battery, if you well, we'll see the chemical reaction that we do for batteries. All right, I think you all should have done electrolysis already in chemistry. Have you all done electrolysis?
Not yet, please.
Not yet. Oh dear. All right, hold on. Let me just put up reactions so you all can Give me top and bottom. Right. Okay, cool. Okay, well, I might probably beat you all to electrolysis. And then we have um, nuclear energy. They gave us the big examples here, but there are tons of other examples of nuclear energy. We have nuclear fusion, which is what the sun creates its energy with, and then we have nuclear fission, which is the energy in the center of the earth. Two very different things, but we will go through this when we start doing modern physics. That's the very last topic we're going to be doing. So you see how I say, or why I say physics is the study of energy and everything contained within it, because that's all physics is. That's everything that's contained within physics and more. Law of conservation of energy. This is one law you all have to remember and have to know by heart. It's like 10, 15, 10, 12 words, not that hard. So what is the law of conservation of energy? Simply, energy cannot be created nor destroyed. That is our law of conservation of energy, meaning we cannot create energy nor can we destroy it. What it does, it simply is converted from one form to the other. You see here how we have all these different forms of energy. Energy can created or energy can go from one form, right? We can take all this energy and one can be converted to the next and another one and another one. It can go in a whole line of succession. So that's what happens with energy. Energy, we cannot make energy. We cannot destroy energy. What we can simply do is convert it from one form to the other. So reading, many times when energy seems to be lost, it's it is converted into a form that we cannot utilize or observe. There are lots of times when energy is lost in a system. Sorry, I heard a sound. Right. Okay, sorry. All right. There are many times when energy is lost in a system, and that is usually because, right, it's being converted into something that we cannot see or utilize. It's kind of like, if you did some work and your mother don't see you doing it, she'll think that you didn't do anything. We go through that every day, don't we? Right? The instant you sit down on that couch, oh gosh, look at this, sit down on the couch all day and do nothing in my house. It's the same kind of thing. If they don't observe or see how the energy is being utilized, we can think that it's being lost or nothing's being done. But not really. It takes a little more energy to identify where we have our different forms of energy. So let's look and see what are some examples of energy transformations. All right, so here I have a couple of examples. Let's make this a wee bit bigger. So let's see what we have. We have simple energy, chemical energy here. Let's look at it. You eat some sugar. All right, well, we are so used to eating sugar now, we don't even notice the amount of the sugar rush. But anytime we eat something with sugar in it, or behave, sugar or, yes, question. Well, you just left your mic on. Right? So anytime we eat something, our body burns that food or converts that food into simple carbohydrates and sugars for our body to utilize it. What is the process of converting food into energy? Biology and chemistry. Come on. Start with R. Anybody knows the process of converting simple sugars into energy in your human body? It starts with R. Respiration. Right? Respiration, we take in oxygen, and with the presence of enzymes, we burn the carbohydrates in our system to create energy, water, and carbon dioxide. You all should have done that chemical reaction. All right, so this is a chemical Right. So that's what I said R. So this is where you see all your physics topics, one jumping into the next one because they're all related. All sciences are related, even though physics explains everything properly. Right. So we have chemical reaction into motion. So you use the energy that you get from food to walk and to move. Right. Yes, we eat 3 to 4 meals a day, so we don't really have that issue and problem of not having enough energy to move. But when you have people or animals or anything who don't have or don't eat enough, all right, they will not have the energy to move properly. Okay, so you do need energy from food, and we can get that by chemical reactions in your body. All right, then we have, look, we have here radiant energy. That is, you get energy from the sun. That energy travels through space, enters our atmosphere. The leaves in a tree will absorb that sunlight, and by the process of what does it create energy? What is the process that plants create energy from or with? Starts with P.
Photosynthesis.
Photosynthesis. Photosynthesis is the process by which a plant uses chlorophyll to convert um, the starches and water into energy that the plant can utilize. And it needs to do this with the presence of sunlight. Sunlight here is the catalyst that drives that reaction forward. So that's why in the nighttime, a plant will not undergo the process of synthesis or photosynthesis, but it will then go ahead and do what? What energy transformation do plants go through in the nighttime? Y'all, how do plants utilize energy in the night? Starts with R. I just said it.
Respiration.
Respiration. You should know this. This is both biology and chemistry. All right, so you see how we can look at our energy conversions, and this is where we look at the processes by which energy is used. Here, we just look at how the energy is transferred and different types of energy that are being done. We have chemical reaction, meaning we take petrol or we take gas or whatever. It goes through a chemical reaction in the engine of a car and it creates motion. We have electrical energy. Electrical energy can be used to heat up the coils in a stove, an electric stove, and create thermal energy. So you see how we can use one form of energy to create another type. Look, we can have even a big, look at how this can be converted all over. If we just did that. We have food. Food is converted in by chemical means into physical work. So we get energy by chemical reactions. We can get a big, huge one here. Look, this one here, they used, is that oil? No, that is not oil. That looks like nuclear, but you can still use it as nuclear. All right, so suppose a nuclear power plant generates energy. Or this is not supposed to be nuclear. This is supposed to be oil. I don't know why they have the wrong sign. So oil, you burn oil or gas, and that is chemical energy, and we can use that to be converted into mechanical energy such that we can use it to launch a shuttle or whatever. All right, then we can use it to convert electricity by running through power plants. We will go through how power plants, and actually that'll be one of your homeworks. Read up on how power plants in Trinidad create energy. All right, I'll write that down just now. We have here that energy can be converted into electrical energy. We can convert it into energy that a car can use, because oil and gas go straight into cars. So you can see how energy can be converted to many things down the line. I think I had a next diagram. Where did that other diagram go? I have no clue where it went. Oh well. So those are the type of energy. You all have to learn how to take your energy and see where they are converted and how they are converted. So you're going to get some questions. I like that. I'm going to post up some questions or some examples on how to do energy conversion sequences. All right, so that's going to come up sometime in the Google Classroom. So let's look at the two different types of energy that we need to know how to calculate at this level of physics. There are far more types of energy that we calculate, but in mechanics, we only look at two at CSEC level. So we're going to look at kinetic energy and we're going to look at potential energy. So reading, objects and bodies require energy to move. This is be like, well, yeah, if you don't have energy, you can't move. We know that. All right, we say that every day. Boy, I had no energy to do nothing today. How many of you all said that this morning or yesterday? Right? I am pretty sure somebody said that exact same thing within the last few days. I have no energy to do nothing. Number one, we massacred the English language doing that, but whatever. But that is basically us saying a term in physics or something, an actual physics process. You need energy to do something. So without energy, work cannot be done, and you need energy to do work. See how you all use physics terms or physics sequences in your regular conversation and you don't know it? So the energy utilized by moving objects is called kinetic energy. All right, so this is our first term to learn. That marker is too dark. All right, so we have kinetic energy. And what is kinetic energy? Kinetic energy is simply the energy being used by a moving object, body, or system. All right, a body tends to be, we can talk about a human body or an animal body or something, an object being an object or a system being a whole sequence of things. So that is why I tend to say object, body, and system, because they're all the same thing, but they refer to different situations. This is also measured in joules. Remember, I said all forms of energy are measured in joules, and joules are extremely important in your topics because you get marks for saying you're correct. Your correct units. I don't want to be losing marks for something that I don't have to calculate. Remember your units and please put them down when you use them. So how do we calculate kinetic energy? Kinetic energy is simply half, as in 0.5, right? Multiplied by the mass of the object in kilograms. So let's put half multiplied by the object in kilograms. It must be in kilograms. If it's not in kilograms, it's not going to work out correctly. Multiplied by the velocity squared. So whatever our velocity is in meters per second, we square that value. So our formula is EK being kinetic energy, E subscript K is equal to half mv squared. So it's a half multiplied by mass multiplied by v squared. Please, guys and gals, I have seen people do this piece of nonsense. They went and did EK is equal to half and they went and did this. Don't do that. Please, don't do that. The v is the only thing being squared in this topic. So it's a half mv squared. Very easy equation to remember and a very easy equation to utilize. Hold on. All right, so then we have potential energy. How does an object get energy to move? Let's think about this really simple demonstration. Real simple. When I tell you simple, guys, simple. Oh, look at this safety here. If I were to take my eye drops here, hold it here. If I let go of it, what's going to happen to it?
It would fall.
It'll fall. And isn't falling moving?
Yeah.
Yeah. Think about nobody has ever thought about this. If I take something and drop it, it is going to fall. So that means it has energy to fall. Where is this eye drops getting the energy? Is it getting from my hand? Do you think my hand is getting tired and transferring energy to the eye drops?
No, the gravitational pull.
What happens? We know on planet Earth or on every large object in the universe, gravity exists. And gravity tends to pull all objects towards the surface. No matter where I am on this planet, if I were to drop this bottle of drops, it is going to fall down. And why does it fall down? Because gravity pulls it down. So that means because of gravity, this bottle has some energy stored in it. No, we're not talking about the chemicals in the eye drops. We're talking about the bottle itself, right? This bottle here, if I hold it here, gravity is giving it some of, it's making energy being stored in it. You all ever notice if you were to drop something from a small height from here to here, it's not going to feel like anything much. Well, let's take something heavy. I have a rock. That's why I have a rock on my table. Okay, it's a very pretty rock. That's why. Right? If I were to take this rock and drop it from here to here, I'm going to feel the weight in my hand. What's going to happen if I take the rock from a high distance and drop it on my hand? Is it going to feel like this, or is it going to kind of hurt? It's going to what? It's going to hurt. Suppose I drop it from here onto my foot. Number one, I'm not going to do that because it's probably going to bust my toe. All right? So energy in a object depends on how high it is above the ground. You all ever heard of the story if you drop a coin from on top a very high building, you can kill somebody? You ever heard of that?
No.
No, go and read it up. If you drop a coin, there's this little myth. If you drop a coin from on top the I think it's the Seattle Needle. There's a very tall building that they call the Needle, Space Needle, I think, in Seattle. If you drop it from the top of that building and it hits somebody, it can potentially puncture their skull and kill them. A simple coin, as in a 25-cent piece. Right? Now, what that tells us, or what that is a demonstration of, depending on how high you are above the earth, you can have more energy than if you are very low down. We all know that, right? If you take something from right here to here, you feel nothing in your hand. Okay, let's take the heavy rock. You can actually hear how heavy that rock is. Probably a good pound, 400 grams. All right, so if I drop it from here to here, I can feel it. If I drop it from a good distance, I hope it'll bounce. You actually heard it hit my hand. And ow, it kind of hurt a little bit. Depending on how high something is above the ground, it can have more energy. Why? Because gravity has to pull it down further. And when it has to go further down, that means it's going to gain energy, right? Or it's going to have more energy to travel a further distance. That kind of blowing your mind. Think about it. Yeah, if it has to travel a further distance to fall down, right, then that means it must have a higher energy if it's higher up. We never really thought about it that way. If something has to travel a far distance, meaning to fall really far down, that means it had a lot of energy stored inside of it. So let's go back to the handout. So let's continue reading. How does an object get energy to move? It cannot create this energy. Remember, we just did conservation of energy. Energy cannot be created. It can only be converted from one form to the next. So it has to be present in some form for the object to utilize it. The simplest explanation is that objects can store energy. All right, so that is what we're going to look at here. We're going to look at the fact that objects can store energy. There is, in fact, there are, in fact, many ways an object can store energy, and the most common form of stored energy is potential energy. Folks, the English here is going to tell us that that is what it does. When somebody tells you, we talk about plain, simple English, and I want somebody else to answer. When I say you have potential, what do we talk about? What are we referring to? in regular language?
Like the ability to do something.
The ability to do something. Are they talking about you doing something right now? Or are they talking about you possibly able to do something in the future?
Mhm.
You know, look at the possibility of you being able to do something in the future. I know if you're holding something to use it in the future, isn't that storing it?
Yeah, kind of.
Yeah,
Yeah.
kinda, right? We're trying to get the words and see how the physics and the actual meaning of the word do tie together. Potential means the ability to do, to possibly do something. And here, potential energy means to store energy to use at a further date or time. Kind of the same thing. Potential means to do something in the future, right? Not something that you do right now, to use something further on. So in mechanics, there are two types of potential energy we can consider. One, we have gravitational potential energy. This is the energy as a result of gravity, because we know everything that is above the ground, once we release it, it's going to fall down. Then we have two, we have elastic potential energy. Everybody knows this. If we were to take something elastic and stretch it, if you look at my small video feed, take your elastic hair tie. If I stretch it and I let go, is it going to remain this stretched out? No. What happens is energy stored within the molecules of something that is being stretched. And when we let it go, it goes back to the original shape. So elastic potential energy is where the energy is stored in something that is being stretched out. We don't really look at it at CSEC level. So say at the CSEC level, we only look at gravitational potential energy, meaning we have to calculate it. At CAPE, you have to calculate potential elastic energy. All right, so let's go on a wee bit further. So here, if I have a brick, we just went through it. If you take a brick, hold it above the ground, it has the potential to fall, meaning gravity is going to pull it towards the ground. So that means it has potential energy. If it falls on the ground, is it going to do anything? Is it going to fall any further? No.
Mhm.
All right. So if something is on the ground, it's not going to fall any further. It's not going to go down any further. So how do we calculate potential energy? Very, very, very simply. Potential energy is the mass multiplied by the acceleration due to gravity multiplied by the height above the ground. So our equation is EP is equal to mgh. And at your level, what is the value of g again?
Okay.
10. So look how
Miss,
easy.
yeah, I
Yes.
saw G was 9.8 the other day when I was watching some notes. That was for like a specific topic.
At your level of CSEC, because we don't want you to be that precise, we say let's use a 10 approximation. But the actual value of gravity, which is the average value, the calculated value around the planet, is 9.8065 something, or 9.81. At CAPE level, you all have to use this value. But for CSEC, let's make life easy. We round this up to 10. So at your level, you use 10 unless otherwise instructed to. So 9.81 is correct. 10 is correct. All right. At CAPE, you will see how we get the 9.8065. I'll show you. We actually can calculate the value of gravity on the planet because it's not the same all over the planet. I think the gravity in the Caribbean, if it's 9.81 all over the planet, is 9.72, I think. Yeah, that's the gravity or the value of gravity in the Caribbean. And the reason, because due to that, is geology. The thickness of the crust and the amount of rock that is below us is different than in other places. All right, so anyway, mass is equal to gravity by the height above ground. Why we just said that? Because let's look here. If I have an object of mass m and it's some distance above the ground, it's going to have a potential energy of mg a. Sorry, how did that happen? Oh, I didn't know I could do that. All right. So if you have an object that is some distance above the ground, this could be 1 meter, this could be 10 centimeters, this could be 100 meters, whatever distance is above the ground, the potential energy is going to be the mass by gravity by the height above the ground. Now, once my object has reached the ground, right, my height will be zero, meaning it's sitting on the ground. It has no centimeters or meters above the ground. So if my height is zero, meaning on the ground, your potential energy, let's look at it, will be mgh, and anything multiplied by zero is how much earlier?
Zero.
Is zero. So if I have mg by zero, no matter what your mass is, no matter what gravity is, as in what planet we are on, or moon, right, you're going to get mg is equal to zero. So once you are on the ground, your potential energy is zero because you are no longer above the ground. And the only way you can have potential energy, you have to be some distance above the ground so that you can fall. You can't fall when you're on the ground. Okay, let's not talk about us clumsy people who can stand up and still fall down, right? Right, let's not talk about that. But once an object is on the ground, say my rock, my pretty rock here is on the ground, it cannot fall any further right now unless I happen to dig a hole under it or the earth opens up and it falls. All right. Um, so that's to look and see how we have potential energy and kinetic energy related to each other. Potential energy, this is stored energy. This is the energy when an object is not moving. Well, not really, but when an object is, say, if you're holding an object above the ground, it's not moving, it has stored potential energy. And in the energy increases based on the position and height. So the further up we go, the more energy that object can have. Kinetic energy, this is the energy of motion, and it increases as motion increases. Why does it increase as motion increases? Because EK is equal to half mv squared. So if something goes faster, that means it's going to have a greater kinetic energy. And here for potential energy, EP is equal to mgh, right? The right, when this goes higher up, the higher we go, the greater potential energy we will have, and vice versa. If we go slower, we're going to have a smaller kinetic energy. If we get lower down on the ground, we're going to have less potential energy. Energy conversion. Energy is easily converted from kinetic to potential and vice versa. So we can take kinetic energy and it can be converted into potential, and we can take potential and convert it into kinetic. We must be able to identify and calculate these conversions. So let's look at here. Let's see what we have. Say I have an object with some distance, some height above the ground. Let's put in some numbers, right? It's 10 meters above the ground, right? My object has a mass of 1 kilogram. So when it is at the top here, I'm holding it 10 meters above the ground. It's not moving. So if I'm not moving the ball as in it's just there, sitting there, let's see what we will have. Our kinetic energy, right? When it's sitting at the top here, the velocity is 0. So let's see how we get our numbers changing. All right, the kinetic energy will be a half mv squared, which will be a half by 1 by, when my object is sitting on the top of the cliff, sitting, it's not doing anything, it's not moving. So the velocity will be 0. So v squared, 0 squared is still 0. And I'm going to get my kinetic energy is equal to 0. Let us see our potential energy now. Let's look at our potential energy at the top of this cliff. EP is equal to mgh, which is the mass by gravity by height. Anybody want to multiply that fast in their head and tell me what it is? Height above ground is 10, mass is 1, and you all know what G is. 100. 100 joules. So we can see here that the maximum potential energy in this system is 100 joules, and we can see here that the kinetic energy is 0. Now let's use some physics and some common sense and some practical knowledge as this object starts to fall down. All right, so let's say it reaches 6 meters. Is the kinetic energy, no, is the potential energy going to be more or less when it is now 6 meters above the ground? Repeating that, does my ball here have more or less potential energy when it is 6 meters above the ground? Less, right? Because you all can work that out quickly. MGH, M is 1, G is 10, H is 6. So it is now 60. So as the ball falls down and gets closer to the ground, the potential energy is going to decrease. So here we can see our potential energy decreasing. What is happening to that ball? And that ball is now falling down off the cliff or off wherever we're dropping it from. And if it is falling, will the kinetic energy be 0?
No, because it has motion.
Right? The ball is now falling. So because the ball is now falling, it is going to have energy. So it's going to have some degree of kinetic energy. Now we can work this out. I'm going to actually do this in the next class. So I'm going to post up the maths conversion. You're going to see how we can convert the maths here. The kinetic energy here is going to be 40. We're going to go through this next day. We nearly finished the class. It's going to take too long. Right? And then we have the last part here. When the object hits the ground, the potential energy is going to be 0. When it hits the ground, EP is going to be mgh, which is going to be the mass by gravity by the height. And when it hits the ground, the height is 0. So your potential energy is 0. And if you work it out, I will show you how to work it out the long way. As it hits the ground, my ball is traveling at the fastest speed that it can reach, and that speed will give me an energy of 100 joules. So let's just read here. The relationship between kinetic energy and potential energy exists such that the sum of the energies is always equal in a system. It's a really a nice situation here, meaning no matter where I am, the sum of my potential energy and my kinetic energy will always be equal to some value. Remember, every system is different. So I can't say if I drop a 500-gram little pebble from somewhere, you're going to get the same value as a 1 kilogram object. No. But for a given system, the sum of your kinetic energy and your potential energy is a constant. So we can use this in maths. Let's look at here. Or let's continue reading. So when EK is 0, and we just saw that here, when EK is equal to 0, meaning when your kinetic energy is 0, your potential energy was a maximum. Because as my object falls down, that H is going to get smaller and smaller and smaller. So that means the potential energy is going to get smaller and smaller. So wherever I hold an object above the ground, that's the maximum potential energy that system, that current system can have. All right, now if I take that object and carry it to a further height, we're now creating a different question, if you understand what I'm talking about. All right, so if I hold something above the ground, the height that we hold it at is the maximum potential energy you'll have. And because I'm holding it, my kinetic energy is 0. All right, and vice versa, meaning when EP is equal to 0, your EK will be a maximum. Now we're going to go through this next day. I'm going to send you the max in it, so you're going to see it. And you're going to try the question and see what we can get. So that's it for kinetic energy, potential energy, and work. Remember, all of these things are measured in joules. Every type of energy is measured in joules. Does not matter what type. Okay, so we're going to wrap up there with the handout. You're going to get, I'm going to send you an actual maths breakdown of this. And if you want, and I do suggest and I do encourage you all can try the maths too and see how, and to not just see, to see and to prove how EP plus EK is a constant for a given system. So I'm going to send you the maths breakdown on it, and you'll see how they're related. But what you're going to take away from this handout, work is equal to force by distance, kinetic energy is half mv squared, potential energy is equal to mgh, and our law of conservation of energy states that energy can neither be created nor destroyed. So we wrap up there for this. Stop share. All right, and we're going to stop there for the class. I have to take a roll because I'm going to stop the recording.